Okay, we are on 5.3 tangent function. So let's do this exploration, graphing y equals tangent of x. So complete the table of values for the domain. X is greater than or equal to 0, but less than or equal to 2 pi. Give your answers to 2 decimal places where necessary. So y equals tangent of x. So at 0, let's recall tangent of x equals sine of x divided by cosine of x. Okay, so if I think about that relationship, okay, at an angle of 0 radians, I'm thinking of what is that ratio of sine to cosine, right? So sine of 0 is 0, cosine of 0 is 1. So tangent y equals tangent of x at 0 radians is 0. At pi over 4, so remember our unit circle, sine of pi over 4 is square root of 2 over 2, and then cosine of pi over 4 is square root of 2 over 2. Okay, so that is 1. At pi over 2, sine of pi over 2 is 1, cosine of pi over 2 is 0. This is undefined because we're dividing by 0, so this is undefined. Okay, and then the rest of these, if we think about 3 pi over 4, that is pi over 4, 2, that's in quadrant 2. So the sine of x will be, that's a positive square root of 2 over 2. And then a cosine of 3 pi over 4 will be negative square root of 2 over 2. And that's negative 1. And then on to pi, so tangent of pi. So I'm thinking sine of pi, that is 0. Cosine of pi is negative 1, still 0. Okay, 5 pi over 4, so that is over in quadrant 3. Tangent ratio is going to be positive because I have now both of the sine and the cosine ratios are negative square root of 2. Negative square root of 2 over 2 divided by negative square root of 2 over 2. That's positive 1. 3 pi over 2, quadrantal angle. That is sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. So I have undefined again. 7 pi over 4, making my way around the circle. That is in quadrant 4. So the sine value there is negative square root of 2 over 2. And then the cosine value is positive square root of 2 over 2, and that is negative 1. And then at 2 pi, we're back to where we started at 0, so it will be 2 pi. Tangent of 2 pi equals 0. Okay. Now that we have the table of values, let's graph the function y equals tangent of x between in this domain. Okay, first thing I'm going to do is where it says undefined, I'm going to put some asymptotes here. And let's make those asymptotes, yeah, black is fine. Okay, that's one asymptote. Another asymptote. And then another asymptote. As I'm doing this, think about the pattern you see with how often or what's the periodicity of the asymptotes. Okay, so those are the asymptotes. And let's draw in tangent of 0 is 0. So tangent of 0 is 0. Tangent of pi over 4 is 1. Tangent of 3 pi over 4 is negative 1. Tangent of pi over 2. So tangent of 3 pi over 2 is negative 1. Tangent of pi is 0. Tangent of 5 pi over 4 is 1. Tangent of 7 pi over 4 is negative 1. And tangent of 2 pi is 0. If I do tangent of negative pi over 4, I'm going to get negative 1. If I do tangent of negative 5 pi over 4, I'm going to get 1. If I do tangent of negative pi, I'm going to get 0. If I do tangent of negative 7 pi over 4, I get negative 1. Okay, so maybe you start to see the pattern here. So what does this graph look like? Well, if I have asymptotes, it's going to approach the asymptote, and then it's going to be... Okay, first off, it's not a sinusoidal function. It doesn't look like what we've been doing with sine and cosine. It looks completely different. Okay. Okay, so that's graphed. Is the graph of y equals tangent of x continuous? No. Why? Because there are asymptotes. Write the equations of the vertical asymptotes over the domain negative 2 pi to 2 pi. Okay, so if we take a look at our asymptotes, this is x equals pi over 2. This is x equals 3 pi over 2. This is x equals negative pi over 2. And this is x equals negative 3 pi over 2. So what are my asymptotes? X equals negative 3 pi over 2. X equals negative pi over 2. X equals pi over 2. And x equals 3 pi over 2. Write the equations of the vertical asymptotes over the domain, then write the domain of y equals tangent of x. Okay, I'm going to think of this like our, when we did coterminal angles, how often they varied. Coterminal angles, there were different versions of them every 360 degrees. Well, how often does this vary? Well, look at the spacing between, what's that? And that's actually the period, but what is that? That is pi over 2 minus negative pi over 2. What's the space between that? That equals pi. Okay, so when I think about this, write the equation of the vertical asymptote. So this is generally, right? What's a general statement that I can write? So if I start with x equals pi over 2, I know that's this asymptote right here. Okay, I know that that's that asymptote right there. I start with that. How do I make it vary every pi units? That's the asymptotes for y equals tangent of x. That's the spacing between each of those asymptotes right here. How do I make it vary by that much? Well, I can add pi units, but I need a general format for this, so I'm going to multiply by n, where n is an element of all integers. Okay, so when I look at this, if I say let n equal 1, or let's say n equals 0, then x equals pi over 2. That's one of our asymptotes. When n equals 1, then x equals pi over 2 plus pi. Well, that's the same as pi over 2 plus 2 pi over 2. And that equals 3 pi over 2. 3 pi over 2. That's another one of our asymptotes. Let's go the other way. N equals negative 1. That's x equals pi over 2 plus negative pi. Oops, negative pi. So that's plus negative 2 pi over 2. And that equals x equals negative pi over 2. And then so on. You can generate all your asymptotes by choosing different integer values. Okay, so that's the general form. Let me just get rid of this. Write the domain. So the domain, well, it's going to be all x values except for the asymptote. So how do I do this in a nice simple way? So domain, I know it's all x values except for all these recurring asymptotes. So how will I do this? X such that I'm going to rewrite the equation with the asymptote but with a slash through it. X does not equal pi over 2 plus pi n, where n is an element of integers. So there we have it. Also, well, technically, we should also put if that's just integers, yeah, that's fine. It's not an element of, so it's basically what this is saying is this is not, the domain is everything except the asymptotes, which is what this says. Yeah. Okay. Number 6, what is the value of the parameter a in y equals tangent of x? So if I look at this, y equals a tangent of x. Well, a is just 1. What is the value of parameter a? So a equals 1. Does the graph appear to have an amplitude? How can you interpret the value of a? There is no amplitude. There's no maximum, right? This doesn't look like a sine or a cosine graph. There's no amplitude, comma, because there is no max or min value. So the way we interpret a, the a value, is simply the vertical stretch factor about the x-axis. And that's it. Okay, and we'll show you through Desmos later on how that works. Okay, what about the domain and range? So domain, see above right here, and then the range is y such that y is an element of all real numbers. Okay, and we can clearly see that on the graph that it goes all y values up and down. What is the period of the graph? Period is one cycle. Where do I start? Where do I end? At the same point, relative point. So I can go from asymptote to asymptote to define my period. So right here, that's negative pi over 2 to pi over 2. To pi over 2. Well, that is pi radians. So my period is pi. I can also think of it like this. If I go from 0, I can start at 0 right here and go to pi. So I start at the x-intercept and I go to pi. That's also pi radians. Okay, so the period in either case is pi. Next page. Consider the function y equals tangent of 2x. What transformation is indicated as compared to y equals tangent of x? Well, y equals tangent of 2x. My b value is 2. So this is a horizontal stretch about the y-axis. Remember, my factor is 1 over absolute value of b. So that's 1 over 2. So this is a horizontal stretch about the y-axis by a factor of not 2, but 1/2. What is the period of y equals tangent of 2x? So if my stretch factor is 1/2, then let's do this. So y equals tangent of x has a period of pi. If I apply 1/2 factor to the period, then new period is pi times 1/2, or pi over 2. So pi over 2 is my new period for y equals tangent of 2x. Can you establish a general rule for finding the period of a tangent function given its equation? Yes. So for the tangent function, okay, for the tangent function, my period is pi divided by the absolute value of b. Okay, because for tangent, y equals tangent of x, the period is pi. But anytime I change the b value, I change my period by that b value, which I do by dividing by absolute value b. Okay, so in this case, y equals tangent of 2x. My new period is pi divided by absolute value of 2, and that's pi over 2, which is what we determined from before. Okay. All right, comparison of basic trigonometric functions. So let's go through these. The sine function, the domain, x such that x is an element of all real numbers. The range, we know that varies between -1 and 1, so y such that -1 and +1, y is an element of all real numbers. Period of the sine function is 2 pi. The x-intercept, sine of 0 is 0. sine of pi is 0. So every pi n units, where n is an element of I, that's where the x-intercepts occur. The y-intercept for sine function is, you remember it starts at 0, so it's at 0. Asymptotes, none. Amplitude, we know it's 1. The max value is 1. Minimum value is -1. Cosine function. Y equals cosine of x. Well, we know the range, or sorry, the domain is x is an element of all real numbers. What about the range? So this has the same range as the sine function. Okay, there it is. Period, 2 pi. X-intercept, so we know that the x-intercepts occur, so where is cosine of x? 0. At cosine of pi over 2, it's 0, so pi over 2 is where it starts, plus pi n. N is an element of all integers. Okay, y-intercept. We know it starts at a maximum on the y-intercept, on the y-axis of 1, so the y-intercept is 1. Asymptotes, none. Amplitude, 1. Max value, 1. Min value, -1. Okay. Tangent value, the domain. So we had this restriction where basically how we're defining the domain of the tangent function is that it's not the asymptote. So this is what we have, where x is an element, oh, not x, where n is an element of integers. Okay, and then the range is all y values, real numbers. Okay, the period we saw from the tangent function is pi. The x-intercepts for pi, they vary every pi unit. So if I start at pi n and define n as any integer, so if I say n is 0, then the x-intercept is 0, which is true. That's where we have. If n is 1, then the x-intercept is pi. Or if I have n is -1, I have x-intercept at -pi, and so on. Okay, the y-intercept is 0, passes through 0, 0. Asymptotes, well, we know that the asymptotes occur at x equals, so this is in general terms, pi over 2 plus pi n, where n is an element of integers. Amplitude, there is none in a tangent function. Max value, none. And min value, none. Hello, we are over at Desmos. So I'm going to just show you on Desmos live, real time, what happens with transformations of the tangent function. And just so you're aware, transformations of tangent functions are beyond the scope of this course, but they behave the same way. So let's turn this on. So here's the tangent function. Where a equals 1, b equals 1. There's no translations. There's no vertical shifts or phase shifts. So if I go to an a value of 2, well, it's going to stretch it up, right? So it's going to stretch it up. So it's a vertical stretch about the x-axis. So if I go to a equals 5, does that make sense that I'm going to anchor 0.1 pi over 4, 1, right? So if I start at 1, folks, does it make sense that 1, 1 will go to 1, 5, or sorry, pi over 4, 1 will go to pi over 4, 5? Yeah, it does, right? So the x values are what's changed. Okay, so that's the x value. B value, well, that's the horizontal stretch about the y-axis. Well, let me go back to A value. So if I go up, that makes sense. What if I go negative? It flips around the other way, right? So it's like it's a reflection, right? So that makes sense. Okay, so let's go back to A equals 1. Same thing with the B value. If I go B value of 2, that's a factor of 1/2. Does it make sense that pi over 4, 1 will now go to, that should be pi over 1/2 factor, pi over 8, 1. And visually, it looks like that's what happened, right? So factor of 1/2. If I go B value 0, what happens? Well, it's going to reflect across. There it is. Okay, that makes sense. Okay, let's go back to B equals 1. This is my vertical shift. Okay, that makes sense. Just goes up and down. And then this is my phase shift, which goes left and right. So that makes sense, right? There we go. Okay. A couple of things on here. I've turned on some key points. I have y equals tangent of x. And I turned on these key points so you can see for reference, right? So I have 0, 0. That's my x and y intercept. And then negative pi over 4, I have negative 1. Pi over 4, and I have positive 1. If I have y equals 2 tangent of x, that should be a vertical stretch about the x-axis. So let's turn that on. So from here to there, if I vertically stretch it, that should be pi over 4, 2, and that's in fact what occurs. Same thing on the negative side. Negative pi over 4, negative 1 becomes negative pi over 4, negative 2 because of my vertical stretch. If I turn on my vertical stretch where the A value is 1/2, you can see that pi over 4, 1 becomes pi over 4, 1/2 right there. What if I change my B value? There's a B value of 2. Well, I know that's a factor of 1/2, so does it make sense that I have pi over 4, 1 becomes pi over 4, pi over 4, 1 becomes, so the y values are the same, pi over 4, 1 becomes pi over 8, 1. So right there. What about a B value of 1/2? Well, that means it's a factor, horizontal stretch factor about the y-axis of a factor of 2. So it doesn't make sense that pi over 4, 1 is stretched to pi over 2, 1. It does. Okay, and the rest of these are, this is a vertical shift by 1 unit up, vertical shift 1 unit down. This is a horizontal phase shift 1 unit to the right, horizontal phase shift 1 unit to the left. Okay, a couple other things I want to show you here is you can see the horizontal asymptotes happening at pi over 2, negative pi over 2. The class example we had was what transformation occurs when I have tangent y equals tangent of 2x. So right here. So I'm looking at this. Well, that's a b value of 2. So again, b value of 2. That affects the x value. So pi over 4, 1 from the original y equals tangent of x transforms to pi over 8, 1. So right there. And remember we asked what happens to the period. So I'll turn this off. The period we can see from asymptote to asymptote. So negative pi over 2 to positive pi over 2. That's a period of pi. When I have a transform value, the b value of 2, y equals tangent of 2x. That is a horizontal stretch by a factor of 1/2 about the y-axis. So what happens to the period? We said that the period also changes by a factor of 1/2. So pi becomes pi over 2. Well, let's take a look at, is that the case? Well, this is pi over 2. Right here is pi over 4. The asymptote for y equals tangent of 2x is pi over 4 to negative pi over 4. And that distance between those 2 points, so those two asymptotes, is pi over 2. So our new asymptote is pi over 2, and it should make sense that it changes by a factor of 1/2. Okay, anything else? Okay, I'll leave this in the notes, and you can play around with the transformations. But again, transformations for this course, they're beyond the scope of the course, but you should understand that they work the same way as we taught with the other sinusoidal functions and also with just function transformations in general.